Welcome. My name is Blair, and today we're talking about anomaly detection in buildings with machine learning. Buildings are full of data, from temperature and humidity levels to energy consumption and occupancy patterns. This constant stream of information offers a valuable window into a building's health and efficiency. Anomalies, deviations from the expected behavior in this time series data, can be crucial for building management. Anomaly detection plays a vital role in identifying these outliers. It helps us spot unusual spikes in energy use, unexpected drops in temperature, or occupancy patterns that deviate from the norm. These anomalies can signal potential problems like malfunctioning equipment, inefficient systems, or even security breaches. Time series prediction, the art of forecasting future values based on historical data, is often intertwined with anomaly detection. By creating a model of the expected behavior, we can highlight deviations as anomalies. This allows for proactive maintenance, preventing equipment failures before they can disrupt operations, and optimizing energy use by catching inefficiencies early on. Effectively utilizing anomaly detection in time series data empowers building owners and managers to transform their spaces into truly intelligent environments, one that can anticipate and respond to changes, ensuring comfort, safety, and cost effectiveness. To delve deeper, this video will showcase real-world examples of anomaly detection. We'll start by exploring some illustrative examples to grasp the underlying algorithms. Then we'll transition to a practical building scenario, analyzing energy use patterns and CO2 levels to identify anomalies within them. Um, Anomaly detection in building focuses on these three key areas. First, proactive maintenance. Accurate anomaly detection in building time series data enables early identification of equipment malfunctions or inefficiencies. This allows for proactive maintenance actions. This helps minimize downtime, reduce repair costs, and extends equipment lifespan. Next, of course, is energy efficiency. Anomaly detection pinpoints energy consumption anomalies. It really facilitates targeted interventions to optimize building energy efficiency. By identifying and addressing energy wastage, buildings can cut operational costs, lower carbon emissions, and enhance sustainability efforts. Lastly, occupant comfort. Uh, Detecting anomalies in environmental conditions like temperature or air quality ensures prompt actions to maintain comfortable and safe indoor environments. This contributes to improved tenant satisfaction, reduces complaints, and offers a healthier indoor space, which enhances overall occupant experience. Here I made this chart of 8 plots to try to demonstrate how different algorithms are challenged to distinguish between two distributions. The black points are a uniform distribution, and the white points are a Gaussian distribution. Basically, already the viewer can see that some algorithms perform better than others. The angle-based outlier detector basically assumes there's like this angle from the origin to every point, and then sort of clusters points based on that angle. The Gaussian mixture model assumes that the distribution that you're trying to find is Gaussian, and then tries to estimate the mean and covariance to identify outliers. Isolation forest, of course, is a very well-known algorithm based on decision trees, and it uses this really complicated piecewise function to find a boundary within distributions. Next is a cluster-based local outlier factor, and basically this considers every point's deviation from a cluster of centroids and calculates the local outlier factor based on the density of neighboring clusters. Histogram-based outlier detection, very efficient. It sort of sorts points into different bins and then sort of categorizes the bins or anomalous or not. You can sort of see that in the plot very easily. K-nearest neighbors, very good performer here. And it basically looks at a point and then sort of looks at the neighboring points and sort of calculates a metric for that. Very simple, robust, and effective here. Principal component analysis sort of does a transformation on the data, and then sort of finds and then sort of classifies points as outliers if they lie off this sort of axis. And lastly, support vector machine, another really efficient way to find this sort of high dimensional boundary that separates these two distributions. Now we get to turn to some real building data to analyze. Um, Here is the code repository where all this information can be looked at. The link to this repository is in the comments to this video. I'm turning to the README now because it's nicely organized. But I wanted to highlight the open source data set that I used for this analysis. It's from the US Department of Energy and a building from Lawrence Berkeley National Laboratory. It's a multi-year open data set. There's all sorts of different building data. In this one, I'm using the room into indoor CO2 levels, and also miscellaneous electrical consumption from just the sockets in the building. I think these are just like two really interesting data streams that show interesting occupant behavior. You can see here, like looking at just like it's multi-year, just looking at some years, just to sort of condense the information a bit. You can see in 2019 the sensors showing that nice weekly and daily pattern. In 2020, CO2 sensor 22 has this kind of like weird anomaly there, but 52 and 72 again, that weekly and daily pattern is there. The miscellaneous electricity streams are really interesting. They have these nice big spikes, so I'm hoping that the anomaly detection will be able to pick them up and show some interesting results. First, I want to look at unsupervised anomaly detection. Again, this is unlabeled data where we're just letting these algorithms through different data transforms and mathematics highlight outliers. First, we have the z-score, which uses sort of multiples of the standard deviation to flag outliers. We have isolation forest. This is a very popular, well-known algorithm used in enterprises and in production to identify outliers. It's based on decision trees. And lastly, we have the local outlier factor, another quite well-known factor that bases outliers based on sort of point densities. Looking at just a week of CO2, you can see here that the isolation forest kind of sets this threshold for anomalous peaks of CO2 at this sensor. And there's the z-score and also the local outlier factor identified far less anomalies, with the local outlier factor also sort of oddly highlighting these lower bounds of CO2 where the CO2 is especially low. Looking at the electricity consumption, this is very interesting. You see z-score and isolation forest. Again, a bit of a threshold developing there, but very similar points between the two are detected. Whereas in the local outlier factor, fewer points are detected, and you also have some that are very normal, to my eye also being detected and being flagged as anomalous. When we move to the supervised anomaly detection, we used two different types of prediction algorithms to do the regression. We used gradient boosted trees and also a long short memory, which is a recurrent neural network. We did both hyperparameter search and different cross-validation techniques. Those are in the notebooks in this repository. And to make sure that when we are pitting these two algorithms together, they're the most competitive and high performance they could be. Again, so we are trying to predict the next value off historical values, and if there's a big deviation, we can assume that that is anomalous in some way. Basically, we also used a threshold approach of the mean absolute error to identify outliers. It's a very interesting results. Here we see with the electrical data, just a week of electrical data, that the gradient boosted tree identified far less anomalies, whereas the RNN detected pretty much all of them as anomalies. And also here we hear it again for a different week. This is very interesting behavior, and probably the thresholds could be adjusted a bit more. But here we have many flagged, and the same threshold only produces one anomaly detection in the electricity for a gradient boosted tree. When we move to CO2 sensors, a bit more evenly matched here, with many similar points being identified by the RNN and gradient boosted tree. Moving to another week, again, gradient boosted trees has less anomalies detected. I guess as a conclusion to all of this is really sort of interesting behavior, and sort of a next step that I'd want to take is understanding the relationship between the performance of these models and how many points they detect as anomalous, because maybe the RNN is returning so many anomalous points because it's simply more inaccurate algorithm to use. And so that is an interesting conclusion and something to further research in this type of performance. But for now, I will leave it to that. Please like and subscribe and get in contact with me if you have any more ideas or you'd like to talk about this further.